equal to Ct plus let me see, plus Cmax divided beta k plus 1, which multiplies 1 minus Ct divided Cmax beta k plus 1 minus plus, I need to go here, minus Cmax divided beta k plus 1. Because then if I substitute 0 here, it's just 1. Okay, should work. Check what I'm doing. Okay, now I think I can write it in this way, equal to Ct, and then I take a common factor Cmax, Ct plus Cmax divided beta k plus 1, which multiplies, I can write something like this. I can write 1 minus, I put a minus here and then I change sign between parentheses, so it's 1 minus 1 minus Ct divided C max to the power of beta k plus 1. Should be this expression here. This is our integral. And what is the integral? It's the surface runoff. So this is the surface runoff. And the surface runoff is given by rainfall, Ct, minus something. And what is the minus something? It's the storage. So if I want to give an expression for the storage, let me call it Wt. Wt is the storage, is equivalent to Cmax divided beta k plus 1, which multiplies 1 minus Ct divided C max to the power of beta k plus 1. This is storage. What is the maximum storage in the catchment? It's an interesting question. So what is the max for Wt? The max for Wt is obtained if you substitute, instead of Ct, you use Cmax. And therefore you obtain that Wmax. Here, if you, instead of Ct, you plug in Cmax, you have 1 minus 1 to the power of 1 minus 1, so it's 0. And therefore you just remain left with the common factor Cmax divided beta k plus 1. By the way, here, again, you see that it corresponds to our preliminary intuition. If you plug in here for beta k 0, you obtain that the storage, the maximum storage is equivalent to Cmax, or the maximum volume stored into the catchment is equivalent to Cmax. Fine. If you plug in for beta infinity, you see that you have 0 storage into the catchment, which means that the catchment is impervious. compressing periods. Okay. For the sake of model application, it's useful to invert one of these expressions, and in particular the expression for WT, in order to give an explicit expression for CT depending on WT. This is easy to invert. We don't make the inversion step by step. I just want to show you, it's here. It's easy, of course. In order to invert this, you need to take the power, you have to elevate the whole expression to the power of 1 divided beta k plus 1. And in fact, here you see that you have something elevated to the power of 1 divided beta k plus 1. As I said, this is very simple. We don't make it step by step, okay? Because it takes like 5 minutes and that's it. It's very simple. Now, we have all the means to apply our model to compute step by step surface runoff and storage, okay? Because you know, CT is rainfall, and therefore I have all the means to compute storage step by step, and then surface runoff. Here, this is the sketch of the IMOD model that was proposed by the person who developed it. So here we have a representation of the integral of the curve. Just keep in mind that this, I'm proposing to you this sketch because this is the original, as I said, sketch of the IMOD model. Unfortunately, this graph is not so easy to understand because with respect to mine, the axes are inverted, and so you see FC in the abscissa, and he wanted to depict the progress of FC as the inverse of what I proposed to you. So from 1 at the origin to 0. What is the reason why he wanted to do this? Because he wanted to assimilate the catchment to a tank. He wanted to propose an analogy with the linear reservoir. And therefore, you see that here, the catchment is indeed depicted as a tank with the maximum storage Cmax, and the limit, the upper part of the tank is not a horizontal line, but it's a curved line according to the function that gives the progress of Fc depending on Cmax. So he just wanted to say, okay, it rains over the catchment. If this is the amount of rain, this is storage and this is surface runoff. Because it's out of the limit of the tank. Again, when you get a rain that is equivalent to Cmax, this is storage, you see WT, and what's out here, it's surface runoff. So it's not easy to understand. So when I explain this model, I don't use this sketch because, you know, it's more conceptual because it makes the catchment schematized through something that is similar to a tank, but it's not easy to understand, in my opinion. And then here, you see that in the sketch he puts something that goes out from the storage for evaporation, ET. We will see how to deal with it. And then he proposes a scheme that we will see in order to transfer the runoff, you see this is runoff, to the closure of the catchment. We will see how the scheme works. It's very simple. Okay, now let's see how the computation is actually performed. we need to split the computation in two parts. The first part is up to saturation. The second part is after saturation. And the second part is easy because, of course, it's everything it rains, it's transformed into surface runoff. In fact, you see here that there is a rectangle, and he calls this contribution to rain after saturation ER1. So there is a contribution ER1. ER1T, which applies when Ct is greater than Cmax, or let's say when rain is greater than Cmax. Let me write it in this way. When Ct is equivalent to Cmax, Ct can never exceed Cmax. So when Ct is reaches Cmax, I have this contribution. Before than that, I don't have this contribution. And then there is a contribution ER2, he calls it ER2, which is equal to, it's equal to C at time t plus dt, or delta t, minus Ct. This is rainfall between at time t. It's rainfall at time step t, because you get the rainfall at the subsequent time step minus rainfall at time t. And this is what rains. And then you have to subtract the storage. So minus W at time t plus delta t minus Wt. Of course, delta t must be very small. Let me go to my web page, because here the slides are very synthetic. Just 1 second, I get the web page displayed in a useful way. Okay, I just want to make sure that everything, I use the same symbols. Okay. So this is a formal expression at each time t for getting ER2. Let me give you a formal expression also for ER1 t. We can write it in this way, and it's, let me write it in the same way, max. It's the max between Ct plus, let me indicate rainfall, cumulative rainfall as with the symbol Pt, minus Cmax 0. Let me explain what does this mean. This is something that is useful when we need to write an algorithm for computing the surface runoff. So what does it happen if at each time step we sum storage plus incremental rainfall minus Cmax. It may happen that storage plus incremental rainfall is greater than Cmax, which means that catchment reached saturation, or it may happen that, again, storage plus rainfall is lower than Cmax. So if I compute storage plus rainfall minus Cmax, either I get a positive number or a negative number. I get a positive number if the catchment reached saturation, a negative number if the catchment didn't reach saturation yet. So if I take the max between C plus P minus Cmax and 0, I am sure that I compute a contribution ER1 only when the catchment reached saturation. So if I write an algorithm to compute surface runoff according to these two expressions at each time step, where rainfall, where PT is rainfall in each time step, so if I write an algorithm that computes at each time step ER2 and ER1 according to these two expressions, that's the target. The sum of these two is surface runoff, and this one may be 0. This other one is not 0, because when it rains, or let's say maybe 0, maybe still be 0, but at a certain point, typically if the curve of the catchment starts from the origin, 1 Cmax, if it starts from the origin, it means that this is never 0 when it rains. Okay. So at each time step I can compute the surface runoff. But there is to say that at this stage we need to introduce evapotranspiration, evaporation, water losses. Because at each time step it's true that it rains, but it's also true that I have some evaporation. And also I want to apply this model also when it doesn't rain. So, you know, if it doesn't rain, you don't have this component of surface runoff production, but I have evaporation. Evaporation decreases the storage. And therefore, it means that in this curve here, I'm not always moving forward. I'm moving forward along the curve when it rains, and when it stops raining, I have evaporation brings me back, meaning that the storage in the catchment goes down. And therefore I am moving back in the curve. And I may get to the point where I don't have any more storage into the catchment. So when it rains next time, I have to start from 0 in the curve. So the moral of the story is, at this stage, I need to introduce a way to compute evaporation. Keep in mind that in hydrology, we usually don't talk about evaporation. We say evapotranspiration, which is the merge of two phenomena, two processes: evaporation from liquid surfaces and transpiration by vegetation. So we call it evapotranspiration. Evapotranspiration depends on temperature, depends on the vegetation, depends on wind, because evaporation, you know that it's conditioned by wind velocity, etc. Evapotranspiration is usually computed by means of empirical formulations.
integral of the curve, we get WT, you call it storage. But isn't the storage like the area above the curve? Didn't we like calculate the area below the curve?
Yeah, the area below the curve is the surface runoff. But if you compute the difference between rainfall minus surface runoff, you get the storage. And this is an average storage over the catchment. So let me just go back here. Okay, so we computed the integral, which is the area below the curve. The area below the curve is given by, it gives to you the contribution to runoff, because again, it's the multiplication of rainfall times proportion of saturated area. So what you have above the curve goes from the curve to 1. 1 is the remaining part of the catchment. So the remaining part of the catchment is still absorbing, and therefore this goes to storage into the catchment. But the difference, keep in mind the difference between WT and CT. CT is storage in the area that are not yet saturated, which is equivalent to rainfall from the beginning of the event. WT is the overall storage into the catchment, which results from areas that are not yet saturated and areas that are already saturated. Okay, but is it clear to you that the area?
Yeah, it's clear.
Okay, perfect. Okay, now we need to compute evapotranspiration, and as I said, it is evaluated empirically. I'm not giving any detail on empirical computation of evapotranspiration, and I don't ask anything at the exam, because this is basically something that is taught in the hydrology courses. But I just want to give you a very brief background. So, again, first information, it is evaluated empirically. What do we evaluate empirically? Empirically, we evaluate what is called E, P, and time T. And what is EP? P stands for potential. It means that this is evapotranspiration provided I have plenty of water available to evaporate. Okay, because you understand that actual evapotranspiration may be zero if you don't have anything to evaporate. So when they decided, scientists, researchers, to study empirically evapotranspiration, they realized that in some conditions there is nothing to study. So they had to study the process empirically when they may have evapotranspiration. And therefore they decided to give to some plots plenty of water in order not to limit evapotranspiration because of lack of water. They wanted to study it under the assumption that there is plenty of water for vegetation to transpire and for evaporation to take place. So they set up in the lab some plots, artificial plots, they put vegetation there, and they measured wind, temperature, but they gave plenty of water to the vegetation. And this is evapotranspiration that doesn't depend on amount of available water, only depends on the variables that condition the process, namely temperature, wind, vegetation, etc. It's a way to reduce the complexity of the problem, and they called it potential evapotranspiration. Again, I'm not asking this at the exam, there is nothing on my web pages. I just wanted to tell you that we have empirical formulas of different level of complexity in order to study this potential evapotranspiration. And then we know that actually this potential evapotranspiration occurs only if we have plenty of water available. Okay? Now, let's suppose that we have a formula for potential evapotranspiration. So, I don't say anything more. Okay? What is a way to compute actual evapotranspiration? Into a model, a usual assumption that is done is that you have actual evapotranspiration ET that is equal to 0 when WT is equal to 0. So if you don't have any storage into your catchment, actual evapotranspiration is 0. Okay, good. This is quite easy to understand. And then, what we typically do, there is a complementary assumption. The complementary assumption is that ET is equal to potential EPT when WT is equal to W max. So if the catchment is completely saturated, it means that there is plenty of water, and then, okay, we take evapotranspiration. So let me draw a graph of actual evapotranspiration. So this is ET, which varies from 0 to EP time t, and this is storage WT from 0 to W max. Okay, this is my graph. Of course, I already said that the graph starts from the origin and goes to this point here. These are the extremes. ET equivalent to EPT when WT is equal to W max. ET equal to 0 when WT is 0. Good. And then the easiest assumption that we can make is a linear progress between these two extremes. This is what IMOD adopts. If you want to see the relationship, it's not here, just 1 second. This is the expression, and it looks complicated, but it's nothing more than what I just presented here, with the difference that here, you know, W max is represented as C max divided beta k plus 1. As we already highlighted just half an hour ago, we said that W max is equal to C max divided by beta k plus 1. And this is nothing more than a linear relationship. Just try to substitute for W 0. If you put 0 here, then you have, this disappears. 1 divided by 1, because 1 minus 1, 0. ET is equivalent to 0. Fine. Let's now put here W max, WT equal to C max divided beta k plus 1, which is W max. Then this goes to 0, it remains only 1, ET is equal to EPT. Perfect. This is what you see here. Okay? But just learn this, please, because this is the only thing that I may ask about evapotranspiration. I may ask you at the exam. Just how do you represent evapotranspiration in IMOD? And also, this needs to be written in the program. There must be a line in the program that computes ET. Okay. Now there is a bit of complication from a computational point of view, because at each time step you have to account for this. So at each time step you have to compute ET, and then you have to subtract ET from the storage into the catchment, because this is something that depletes the storage, brings the storage at a lower level. So we have, at each time step in the model, in the program, we have to compute WT as a result of rainfall, if there is rainfall. So an increase of WT. But then, at each time step, we have to decrease WT by ET. So this is a bit of a complication from a computational point of view, because at each time step you have to first update WT by increasing it if it rains, and then you have to update it by decreasing it due to evapotranspiration. So it's a complication from a computational point of view, nothing complicated conceptually. But from a computational point of view, it's a bit of complication. So, let's see how we can do this. And let me bring you back to this curve. Okay? This curve was depicted by assuming that I have only rain, no evapotranspiration. So at each time step, I increase CT by rainfall, and I compute contribution to runoff and storage. I increase the storage into the catchment at each time step. Okay, this is fine. Now, given after this computation, I have to compute evapotranspiration and subtract it from the storage. What does this mean? That not everything that I see here is increasing the storage. There is also a decrease, which means that a decrease in WT implies it's easy to compute the decrease, because I first update WT and then I subtract evapotranspiration. Okay, this is very easy. But then, if I have a decrease in WT, I have also a decrease in CT. So at the end of my time step, I have to compute the new value of CT. Because you remember that WT and CT are related to each other by an expression. Let me remind it to you. This is the expression that we inverted to compute CT depending on WT. Okay? And this is the expression that gives to you WT depending on CT. Now, given that at the end of my time step I decreased WT by subtracting evapotranspiration, then I have to recompute CT by using the new value decreased of WT. And this is why I told you, let's compute the inverse. Because I told you, we need this. Later on, I'll explain you why. So the precise reason, the very reason why we need this expression of CT depending on WT is that we need to update it after subtracting evapotranspiration. It's just a computational complication. And now we are ready to propagate the runoff to the closure of the catchment. But before I move forward, this is a final detail, let me bring your attention to the sequence of computation that I just mentioned to you, because you may tell me, what is the reason why you first increase the storage, you first compute runoff, and then you subtract evapotranspiration? Could we take the other way around? Namely, could we first subtract evapotranspiration and then compute the storage and the runoff? The answer is yes, you could do this. And actually, if our computation is fine enough, we should get the same result. We are not getting the same result because we are working for finite differences, not with analytical computation. Basically, as you see, after computing analytically the integral, the application of the model is done step by step, finite differences, and then I told you, let's suppose that these intervals are very small, because otherwise you introduce a numerical approximation. And the numerical approximation is just given by the fact that you have to decide whether you have to first compute the runoff or evapotranspiration. It changes, indeed. It changes because it's equivalent, as in a real process, you assume that you have first rain and then evapotranspiration. No, you have together rain and evapotranspiration. And this is the reason why numerical integration gives to you an approximation, because you need, in numerical integration, to decide the sequence and the sequence of these processes. And we basically address this uncertainty by saying, let's adopt a small time step. Anyway, this model assumes that you first compute runoff and then you subtract evapotranspiration. It doesn't change much. You could check personally when you will apply this model. You could check. You just need to invert 2 lines into the program. You could just check what happens, and you will see that if you work at hourly time step, usually doesn't change anything.